Okay, good evening. Welcome to Journal Club number 5, I believe, and Riley O'Hagan's going to present on a slower decay of landfalling hurricanes in a warming world, which is about climate change, which all of you know is a hoax. So it's like, how vaccines don't cause autism. It's a hoax. And if you don't get my sarcasm, you don't know me. Okay. Let's see. Ms. Lipp, was there anything you wanted to add before she began?
If you read the paper, you will have kind of seen some things. It's a broader scope. It's not just hurricane, but hurricane meaning full storm. So wind, rain, wind shear, wind stress. And so it's talking about all of that decay, not just the massive size of a hurricane or the winds of a hurricane, but it's also talking about wave stress, all of that.
And I would like to consider that. I would like to not consider whether or not you have read the paper. I would hope you did. It's actually a short paper. And it's, again, published in Nature. I don't think that Riley intended that on purpose, but Nature is one of the best journals in the world and has some of the coolest science. So hopefully this lives up to that. All right, Riley, take it away, and I'm going to mute myself.
Okay. So my paper is Slower Decay of Landfalling Hurricanes in a Warming World. So they aim to provide evidence that warmer waters slow the rate of decay of a hurricane, meaning the hurricane will take longer to weaken once it hits land. Hurricanes are fueled by moisture, and warmer water provides more moisture and humidity in the air. So the warmer water, the more fuel, and the more intense the hurricane. So the studies were North Atlantic hurricanes that made landfall. So I guess the reason it's North Atlantic is because we're in a temperate region, and the warmer water and humidity from the equator is blown west on the trade winds, and then as the warmer air and water, or as the warmer air rises, it cools within the temperate region, which is why the East Coast gets more rain and why the hurricanes are affected by the warmer waters. So the path of the hurricanes are shown here in figure 1A, which is, again, the East Coast because of how the weather cells carry the moisture. So using the measure of the hurricane velocity on its first day after landfall, they were able to calculate tau, which is the little t in figure B. And it's used differently in different situations, but here it's the decay time or the rate of decay of the hurricane. So the larger the tau, the slower the decay. So with that being said, looking at figure 1B, it shows that in recent years, which are the red lines and the red bars, there have been a higher frequency of hurricanes, and more importantly, that the hurricanes have higher tau values, meaning they decay slower. So the tau has increased 94% in the last 50 years. So like 50 years ago, a hurricane one day after landfall was only at 24% of its initial landfall intensity, but now a hurricane would be at around 48% of its initial intensity. This means the hurricanes are more intense, traveling farther, and are more destructive as a result because they have more time to do damage. This is again shown in figure C, which is the increase of tau over time. So the question now becomes, why has tau been increasing? Looking at figure D, the graph shows the sea surface temperature over the last few decades, and it's been on a pretty steady incline. And when you overlap figure D and C, which is shown in figure E, not only have they both been increasing, but they oscillate at similar times, which suggests a correlation between the two. So to try and prove causality, they use simulations of hurricanes in order to isolate the surface temperature as the only parameter, so the other factors like the pressure wouldn't affect the rate of decay. So at 4 different surface temperatures, which are measured in Kelvin, but it's roughly 27 degrees Celsius, 28, 29, 30. They ran a simulation. And once the hurricane velocity reached 60, they cut off the moisture, which simulates complete landfall because it's no longer being supplied with moisture from the ocean. So figure 2A, the intensity at landfall is the same, but the warmer water it was formed with, the slower it decayed. This supports the field observations that tau and surface temperature are directly related, meaning as the surface temperature increases, so does the tau. To emphasize the role of moisture of the decay, figure 2A after landfall, the dry hurricanes, which are the little plus signs, they were ran as pairs, which are the two colors, but the pluses are dry hurricanes, meaning they have no moisture, and which emphasizes that moisture is the link between tau and the surface temperature. 2B shows that the surface temperature and tau are correlated again, and then C shows the moisture because it's the rainfall, so it's just further emphasizing that the surface temperature relates to the moisture, which relates to the tau. And then finally, they disproved other possible factors, such as the translational speed of the hurricanes, which is shown in figure A. So that has not increased over time, so it couldn't have affected the tau. And then also the movement and the paths of the hurricanes has not significantly changed over time. And even though it's different between east and west, it's still increased in the more recent years. So it didn't affect tau going from east to west. Okay, that was all. Any questions?
I just broke a record. Sure. Let's do some clarification. There were some things that Riley said that and the way she said them, I thought were really good. So go to the first figure. I think it was the second figure, but yeah, this one. E and F. What are those again? The way you said it, I wanted to pause and let that sink in for everyone because you said it so well.
So graph E is just C and D overlapped on top of each other.
Mm-hmm.
And they're both increasing, but they're also oscillating at the same time. So they're going up and down.
Mm-hmm. Which would suggest.
Correlation.
Right. It's in the way you said it before, I think was something like that it suggested a correlation,
mm-hmm.
which is a nice, careful way of saying it's not necessarily caused by, right?
Yeah.
Correlation is not causation. But the point of F is to show that relationship is extraordinarily strong. It's extraordinarily strong. You have a lot of those dotted lines around the main line that's running through it are called 95% confidence intervals. And those confidence intervals, most of the dots fall in there or around there, meaning that you can have very high confidence that this is actually a real thing. But I think as you go into figure 2, I think a point that needs to sink in with us is these are simulations, right, on a computer. These are simulations on a computer. So that means that the cross-hatching, that's just a control. In an imaginary situation where the hurricane immediately loses all of its moisture, which never happens in real life. But it's an important negative control because it should behave in the way it does. If it didn't, then you'd be like, wait, something else is going on. But why? Why? I mean, you asked me a question earlier, and now I'm going to pose it to you. Why moisture?
Because that's what fuels the hurricanes and makes it so intense.
Why though?
Because the energy in the warm water. Something like that.
Do you guys all agree with that? right? I mean, in order for water to evaporate, the stuff with the highest amount of energy actually evaporates first. That's like chapter 2 of biology honors, right? So evaporative cooling in some places, right? So as moisture evaporates, Miss Lift, jump in when I say something wrong. As moisture evaporates, it's the high energy particles of water. So they're all getting together as lots of high energy particles, adding energy to that system. But the medium that they leave, which is a body of water, so this happens in the Great Lakes as well, right? So what's left behind in the body of water is the cooler, less energetic thing. If you juxtapose a high energy thing against a cool energy thing, right, a low energy thing, then you end up with this weird potential difference, which also then fuels the storm forward. Or at least that's my understanding of it. Right, pressure differentials.
Yeah, not to mention you're working over multiple mediums. So not only are you doing just water, you're doing the air-sea interface as well as the atmospheric temperatures and water temperature.
Mm-hmm. Right. So this was their main hypothesis, right? Was the moisture thing. So what's tell us again what the point of figure 3 is.
Figure 3 was just to make sure that there was nothing else having, or probably nothing else having an effect on the increase of tau. So this was the translational speed, and that hadn't increased over time at all, so it couldn't have affected, or it likely didn't affect the tau. And then the same thing here, where they tracked the locations of the hurricanes, also didn't change enough to be significantly have an effect on.
Right. And if Miss Liv wasn't driving, she would want to point out that throughout the whole paper, they refer to the W region, the West region, and then the East region, the West region, then the East region, the West region, then the East region, and then in D, they switch it and put region E and then region W, which is, there's no reason to do that. That's kind of sloppy. So those of you who end up writing papers, try to make it consistent all the way through the paper. But I think B is pretty cool because, again, this is looking for a correlation. If something is a flat line like that, are they correlated?
No.
No, not at all. So did you all understand what translational speed was? Because I really didn't. Translational speed, how would you describe that better than I could?
Me?
Yeah.
I'm not sure.
Or Miss Griff, if she wants to save you, I don't, because I have my idea what it is, and I'm just not sure if I'm right.
My understanding was that it was the time it takes for the hurricane to get from like fully over water to fully on land, because the longer it runs perpendicular to the shoreline, the more moisture it can still take up, so it can still gain intensity.
I see. Okay. Is that right, Miss Lift? That sounds right to me.
I think it also has to do with not just moisture, but like using moisture as its fuel source. So the translational time or speed or energy having to do with if it's using moisture from the sea as its fuel source versus using moisture from other atmospheric cells. So like overland cells. I believe that has something to do with it. So not just is it physically on land, but where is its fuel coming from and has it used it or used it up?
Okay. Go ahead, Riley, if you have a concluding slide.
Oh, I do. Forgot about that. So the big point is that tau has increased 94% in the last 50 years, which I said earlier, but it's likely due to the warming sea surface temperatures increasing the moisture available for the hurricanes. And the implications are One point is that theoretical hurricane models might not consider moisture, so therefore they don't portray hurricanes accurately. And then, more important, I would say, is that if the planet continues to warm, the water temperatures will also warm, and the hurricanes will decay and slow down even more, which will have more economic losses because the hurricanes will be able to travel farther inward, which also means, like specifically here in New Jersey, farther away from the coast will keep having more increasingly damaging storms because the hurricanes aren't losing their energy and their impact as fast. Okay, now that's all.
You guys have any questions?
Yeah, I have one. So are like tropical storms, I mean, tropical islands like Puerto Rico included in this? Like in the data?
I think it was mainly landfall in North America.
I think so too.
And actually, didn't it say the northern hemisphere and West Atlantic?
But I believe that the hurricanes actually had to eventually hit the mainland in order to be considered. So if they hit, let's say they spun into the Gulf of Mexico and then spun back out to sea, they couldn't be counted because they don't have the data. They don't add to the data about losing energy over mainland.
Oh, I see.
It does show points here being hit, but I think it was mainly on the land because it's easier to determine its velocity after a day. Whereas I feel like if it was on an island, it would just pass over the island within a day or more than a day.
Right. What was it, like 3 or 4 years ago? Puerto Rico got absolutely devastated by a hurricane that went through it as if it had not hit any land at all, and then just continued on and went up and I think hit Texas. So I think that the data for hurricanes that did hit places like Puerto Rico are in there, so long as they then eventually hit mainland. That hurricane was way bigger than the island of Puerto Rico, so it was never fully on land and dry. That's a good question. Who else?
In the simulations for the hurricanes, how is it that they all ended up having the same landfall intensity, even though they had different temperatures?
They purposely cut the moisture off at once it hit 60 velocity. The velocity was 60.
So that wouldn't happen in like a real situation, right?
No, they probably kept going.
Yeah, right. I mean, it's this in order to be classified as a hurricane, winds have to hit what, 60 miles per hour? Is that right, Miss Liv?
I don't know, but I don't know the exact amount. There have to be sustained winds as well as sea conditions to be counted as a hurricane. But I think with the simulation, yeah, it was once moisture reached a certain part. So they could have reached that moisture very quickly or very slowly, meaning they were different categoried hurricanes. But once they've met that magnitude of moisture, that's when they kind of turned it off.
Yeah. Because they in the paper they do say right away that they actually were considering what we classify as tropical storms. They were just calling hurricanes anyway. But the thing that really struck me was, if you're looking at the difference between the blue line and the purple line on this figure over the ocean, the speed of the hurricane picks up very, very fast on the high energy, high temperature hurricane, and much slower over the low temperature. But that means that it's a hurricane for longer over the ocean in the lower temperature. It's kind of like kind of an enigmatic, unexpected result for me, at least. I don't know anything about this. Do you guys see the importance of this study? If you put aside the fact that it's fake news. Climate change. That doesn't happen, please. There's the senator from Oklahoma, the senior senator from Oklahoma, his name is James Mountain Inhofe. Yes, his middle name is Mountain. He once took a snowball onto the floor of the Senate and said, see, proof that there is no such thing as global warming. It snowed. Look, I'm holding a snowball. And then he also said that if you read the Bible, it says, God says that he'll never flood the earth again. And so therefore he knows this will not happen. And I think that it's important to do climate studies like this, mostly so that I can get on Miss Lift's nerves, but also because we get to kind of expose you guys to facts and idiots who are going to criticize it, right? Like, what is your response going to be when somebody just yells out fake news? What are you going to do? All right, what's your response, Riley? Do you have a response to me if I'm like, who's fake news?
About climate change?
Yeah. You're going to have a lot of people who do that.
Yeah, my dad does.
Especially this year. Like Texas and the South are having a devastating winter. So how can you support climate change when it's so cold?
Because it doesn't just warm the planet, it just increases the intensity of already occurring weather events.
And And what time of year are we in now?
On year?
What time of year are we in now? We're in winter. And it's going to get warmer or colder in the winter.
It's going to get colder.
And in the summer it will get warmer or colder.
Warmer.
So it's not only influencing and increasing localized weather, it's also doing what?
The global temperature is rising, but not the weather. The weather's being more intense.
Bigger differences?
You're going to experience larger changes in seasonal temperatures.
Yes.
Another thing I'd like to point out is that she was able to do a somewhat intense journal entry, and we've kind of lengthened it, but really she was done in 15 minutes. That's a pretty efficient journal club. Yeah. So that's not a bad thing. This is the trap that young new journal club students fall into, is that they think they have to explain everything. You don't. She could have gotten into a nightmarish coverage of all of the equations, which would have interested zero of you. And so I'm not saying that's not important. For some people who like equations and the maths, that might be important. But right now for this, it's more about interest. Like, here's my next question, which I'm going to ask every single one of you when you go. This was published in one of the 4 top sexy journals in the world. Did it belong in the journal Nature?
Yes.
You think so? Why?
Just for its efficient, nature,
Come on. It's efficient nature. What does that mean? Why is it important?
Because it's something that's occurring right now.
Yeah. Riley, do you have an answer?
I feel like I don't think it should have been in it, just because, you did mention that it is all simulations, but I feel like it just felt repetitive, and I know you have to keep proving and disproving things, but I feel like if it could have been summed up in a sentence.
It was not all simulations. The entire first page was all in situ temperatures from previous hurricanes.
I think you
And
just
then
triggered
they
me.
use, yeah, you just triggered me big time. Like, that was like, what, 40-ish years of in situ temperature? Come on. And then on top of that, then they did the modeling, the hurricane modeling, which is in the oceanography marine science world is super sexy, because if you can model when storms are going to happen and where they're going to happen, you're like right up there with a meteorologist and just
And how
predict the
well
future.
does that work? Yeah, meteorologists. How well does that work? Oh my goodness. I got no ice last night. We canceled school. I got no ice. They would not be able to predict what planet we're on right now. They are been so wrong lately. But really, like I thought it was funny when Riley wanted to do this paper. I'm like, wow, because meteorologists are having a banner year this year. They have in living memory, I can't remember a year where they were so wrong so often. And this might be able to help. I mean, my interpretation of it was that as a model with this new thing, it's a new consideration. What was the temperature and moisture saturation as it hits land? Like, to me, that must be, they were talking about it as if it was a new thing that was not used in current models, and that maybe it would help predict the devastating causes. Can you go to your last slide, Riley? Because I found one thing interesting. You made an argument about the economic losses and not instead on human life losses or the loss of habitat or anything natural. You went straight for the money. That's not I would say that is not necessarily a bad thing, because if you want to get people's attention, especially in government, you have to show them the dollar bill, right?
Yeah.
Because politicians are really good at being like, who died? Yeah, whatever. But if you say, yeah, but there was money lost, they're like, no, right? That's because capitalism.
I mean, like, if you think about Katrina or you think about Sandy and all the major hurricanes, if there's one thing that you can do to save money for the amount of loss that happened during those storms, those government officials will jump on it. And if this is the way to prove to them that climate change is not fake, I mean, this could be a good way to dispel the fake news.
So, you know what's kind of interesting to me as a teacher, science teacher, is especially at a Catholic school, is we're always walking this fine line of, we want to talk about facts, but at the same time, is it appropriate for the audience, right? I talk a lot about cocaine. At some point, that's going to come back and bite me, I know. But do any of you feel like we're pushing you towards a political view? Because that is certainly not my intention. It's definitely Miss Lip's intention, but not my intention. I would never push you towards a political view, especially since I keep taking the opposite view. I don't think she's pushing you either, but I'm just kidding. What, like, do you guys feel like you're being, like, does anyone want to defend the position that there is no such thing as climate change? Which I welcome you doing. The only way for us to convince you otherwise is good argument, I think, because I'm into liberal arts. Anybody want to defend that? Riley, can you unshare your screen? That way I'll be able to see everybody.
Did not do it.
Thank you. Anybody have any thoughts about that? Anybody want to defend it? Anybody want to do it for fun?
What you said, why climate change is not real?
Correct.
I'm gonna say it's not real because we've had ice ages, and we've had periods of like warming up. Like there's an ice age, and then the planet warmed up. So it might just be like part of the planet's natural state.
Like a Milankovitch cycle.
Yeah.
That's an argument that's used. Are we in, what's the word? Where in our orbit are we when the northern hemisphere is in summer? Are we at apogee or perigee? Do you know offhand, Miss Liff? We're at perigee, aren't we?
I don't know offhand.
So what I mean is our orbit around the sun actually isn't a circle. It's an ellipse. So there is a point in our year where we are closer to the sun than we are during the opposite part of the year. I'm pretty sure our summers are when it's farther away, and our winters are when we're closer, which would warm up the winters. What's your argument against that, Miss Liff? What I know that's probably the most common argument for climate change not being real, but there's a good comeback, right?
So yes, there are glacial and interglacial periods that frequently have happened through the history of the Earth. However, none at the magnitude that we're currently seeing. So the way that our orbit is oriented now, which is, if it's perigee or apogee, I'm not sure, but the way in which it's oriented now, so the orbit fluxes a little bit, and as it fluxes away, from the sun, that's when we have our glacial periods. And as it fluxes towards the sun a little bit, it just kind of bows a little bit towards the sun. That's when we have our interglacial periods. So we should have been in the midst between a glacial and interglacial period. However, we are now experiencing what we would see during an interglacial period. So we will see more warming, markedly more than we've ever seen before. And it's correlated to the amount of insulating carbon dioxide and other greenhouse gases within the atmosphere.
Right.
So everyone says carbon dioxide causes global climate change. Carbon dioxide is an insulator blanket, and it helps to catalyze the effects of that greenhouse gas warming. Take AP Environmental, and you will find out all about that.
I've said before, I'll get phone calls, surveys and things, and or if especially targeted surveys where if they know that I'm a scientist, they'll call me up and they'll say, do you believe in? And if you've had me before, you know I don't like that phrase at all. Believe in. You have to accept or reject data if you're a scientist, not believe in them. Okay, it's not a religion. But they'll ask, do you believe in global climate change? And I think the responsible answer for somebody like me is, I shouldn't have an opinion about that like that. Why are you asking me my opinion? They're like, you're a scientist. Oh, you want to be able to say that not all scientists agree, right? But you're asking the wrong scientist. I am a neuroscientist. I don't know anything about climate change. My opinion should not matter, because if you go and you ask climatologists and people who study, when Miss Liff studies and stuff, it's almost 100% that they're in agreement. And then if you include yokels like me, then all of a sudden it might drop down to 99% instead of 100%. But it's still like overwhelmingly, yeah, we are changing the climate. Looking at ice cores and things, you're seeing those fluctuations happening, the increase in temperature happening at a rate that really hasn't been seen since the Permian. And we all know how well the Permian ended, right? That was fun times, with the largest mass extinction in the last 500 million years. And we are losing somewhere, the background extinction rate right now is somewhere between 100 and 1,000 times what the rate was in the Permian extinction. So they lost 95% of all species on Earth, and we are 100 to 1,000 times that rate. So I don't know. I don't believe it. It's a hoax. Anyway, so anybody have any further comments? Was this okay? I thought you did a really good job, and thank you for filling in fairly last minute. I really appreciate it. She did us a favor and filled in. So anybody, anything else? Nice and painless. 37 minutes. Not too bad. And this, all of yours can be this way. Okay. I thought that was a good paper. I thought that was really, I'm going to have to get somebody to do a bad paper at some point, just to remind us that not all papers are good, right? That's 2 in a row that I think we did. They're good. And most importantly, Riley agreed with me. It shouldn't have been in Nature. So that's the important. Nature has its own journal called Nature Climate Change. I just think it should have been in there. Okay.
Yep.
All right. Thank you again, Riley. And so you guys know Ms. Oakley's video is up on the website. I will try to get this done tonight so that I'll put it up on the website. AP kids, we don't have a test tomorrow. I kind of mentioned that already, but we're still working on history of life when we'll talk about those extinctions. Anything else? All good? Thank you again.